Today we will be talking about the variational formulation of a beam element. So we will be talking about the classical beam theory, which we will discuss the main assumptions. Also, we can call it Bernoulli Euler beam theory. So let's first discuss the main assumptions of this theory, and then we will formulate our element. So the first assumption is shear deformations are ignored. So there's no shear deformations. So we are only considering the bending deformations. So since shear deformations are ignored, we can just directly say that the rotation is equal to first derivative of the vertical translation. Okay, so since we ignore the shear deformations, we can just say that the strain energy, the internal strain energy, is due to the bending deformations, and we can just write it as follows: integral from 0 to L 1/2 curvature multiplied by EI curvature, which is the moment, and integrated over the length of the volume. So we will only consider the energy due to the bending deformation. The other assumption is the small deformation assumption. So we are saying that the axial strain is equal to du over dx. Here we are using the engineering strain definition. And the curvature is equal to d square v divided by dx squared. And finally, we are assuming the elastic behavior. So by using these assumptions, we will be driving the plane beam, the element matrices of a plane Bernoulli Euler beam element. Now let's take a look at the total potential energy functional. So let's define the beam. We have a beam element, right, under uniform distributed loading. So this is the x-axis, and the deformation in this axis is called u. And this is the y-axis, and the deformation in that axis is called v. This is the section, and that's the neutral axis of that member. Okay, so let's write down the total potential energy functional, and for this case the P is equal to internal strain energy minus the external work. So I will no longer show it as an element. Let's put it here. Remember that in the truss element discretization, we figure out that we can write the total potential energy functional at each element, and the stationary conditions holds for it. So I'm just writing it for a single element now. So that's equal to, from 0 to L, 1/2 EI curvature dx minus from 0 to L W V times dx. W is the magnitude of the uniformly distributed loading. Now, when we look at this equation, the total potential energy functional, we see the second derivative of the displacement of V, right? So the degree of the derivative in these potential energy function is 2. We call it m is equal to 2. So this tells me that the admissible displacement must satisfy C1 continuity requirement. So this requirement is not only the displacements itself, but also the derivative, the first derivative of the displacement must be continuous over and between the elements. So this tells me that v of x as well as v prime of x must be continuous over and between elements. Okay. Now we can define the beam element now. So the trial function that I should choose must satisfy this condition, or it should be a C1 continuous trial function. Okay, so let's define our beam element. So I will be defining the beam element again with two nodes, a start node and an end node J. That's the x-axis and U. Again, let's plot it one more time. That's y-axis and V. And this is the length of the member, L. So our nodal degrees of freedom, I can have Vi here, Vj here, and we will have, let's draw a deformed shape, something like that. So this rotation will be theta I, and that rotation at the end node will be defined as theta j. Okay, so I need a shape function that satisfies the continuity, C1 continuity requirement, and for that we will be using the Hermitian cubic interpolation functions. So the equations and the shapes of these functions are as follows. So n1 in its natural coordinate system, psi, is 1 over 4, 1 minus psi square, 2 plus psi. N2 is equal to 1 over 8 multiplied by length, 1 minus psi squared, and 1 plus psi. N3 is equal to 1 over 4 1 plus psi squared 2 minus psi, and n4 is equal to minus 1 over 8 L 1 plus psi squared 1 minus psi. So these family of the shape functions are called the Hermitian cubic polynomials, and the shapes look like this, and when I draw the shapes you will find them very familiar. So when you draw the n, this is what it looks like. This is equal to 1, and the shape will have the following form, and I'm plotting this as minus 1 and 1. So this is the plot of n1. If we plot n2, again within the same interval, we will see a shape like this, and this rotation will be equal to 1, or the slope of that, the beginning, equal to 1. That's n2. So n3 is this one, and that's equal to 1, and n4 so these are the graphs of the Hermitian polynomials within the following interval. And when you think about it, these are the deformed shapes that we use to derive the element stiffness matrix of a beam element. Okay, so I'm just using them as an interpolation function and plug it into the finite element formulation. Now I can define my displacement field, right? So the V element is my displacement field, should satisfy the essential boundary conditions. So at x is equal to 0, right? Vi, I should say V must be equal to Vi, dV over dx must be equal to theta I. And at x is equal to L, V must be equal to Vj, and dV over dx must be equal to theta j. And remember that these are the essential boundary conditions that we must satisfy. So with this information in hand, I can define the interpolation function as follows. V is equal to n1, n2, n3, n4 multiplied by the end displacements Vi, theta I, Vj, and theta j. And I can simply write my displacement field as the shape function multiplied by the nodal displacement. And this is my continuous displacement field definition. So remember that all these shape functions are written in natural coordinate system. So the transformation between the natural coordinate system and the actual Cartesian coordinate system of this beam element is as follows: 2x divided by L minus 1. Okay, now I need to determine the strain displacement relationship. Of course, here if you take a look at that potential energy functional, I have to relate the curvatures with the given displacement field with this one. Okay? So let's relate them. Curvature, displacement, relationship. So we said that psi is equal to 2x over L minus 1. So d psi is equal to 2 over L dx. But in order to get the curvature displacement relationship, I need the second derivative of the displacement field. Okay, so basically curvature is equal to del square V divided by del x squared, and that will be equal to 4 over L squared d square V divided by d psi squared, and that's equal to 4 over L squared d square n d psi squared, the second derivative of the shape functions, multiplied with the nodal displacement. Now the question is, how did we obtain this relationship? Now let's also derive that. So let's say that I have a function and I want to take the derivative of that function with respect to x. So I'm using chain rule now. So I'm saying the fx d psi multiplied by d psi over dx. So we already know that that's equal to 2 over L. So I can just write it as 2 over L d f of x divided by d psi. I'm taking the derivative of it one more time. D square f of x dx square is equal to, now I'm taking the derivative of this expression, d of 2 over L dx df of x d psi plus 2 over L d over dx df of x d psi. So this part of the equation is equal to 0 because this is equal to 0. So I need to handle this part of the equation. So we already know that d over dx, or this equation, is equal to, let me write it first. So that's equal to 2 over L d over d psi. I'm using the chain rule for d over dx d f of x over dxi multiplied by dxi over dx. Okay, again I use the chain rule, and again we know that this expression is equal to 2 over L. So as a final step, I obtain the second derivative of any function dx squared to be equal to 4 over L squared multiplied by d squared f of x divided by d xi squared. That's the relationship. Right, let's come back to that expression. Now we find out that the curvature is equal to second derivative of the shape function multiplied by 4 over L squared. Okay, and remember that according to our definition, this part of the equation is called our B matrix. Remember that. That's, in that case, that will be the curvature displacement relationship. So we already have the shape functions defined here. We only need to do is take their second derivatives and multiply it with 4 over L squared. Then our B matrix will be equal to one over L, 6 xi over L, 3 xi minus 1 minus 6 xi over L, 3 xi plus 1. That's the strained curvature displacement relationship. Now the next step is to obtain the element stiffness matrices. I'll just call the element stiffness and consistent load vector. So let's first write the expression for the element internal strain energy. So that's equal to, from 0 to L, 1 over 2 curvature, or let me write it this way, the second derivative of V multiplied by EI multiplied by the second derivative of V times dx. That's the internal energy. So let's put the curvature. I can just write it this way. That's equal to d square V over dx square, and that's basically equal to B matrix multiplied by the nodal displacements. So this is equal to, from 0 to L, 1 over 2 U transpose multiplied by B transpose EI multiplied by B times U times dx. Okay, so from our previous expression we can just call this part of the equation as our K element stiffness matrix. So in that case, k element will be equal to integral from 0 to L. EI is constant. That will be B transpose times B integrated over X. So if I change the variables, I have -1 and 1 EI B transpose times B 1 over 2 L d psi. Okay, so again I use this relationship. To switch between dx to d psi. Now let's take a look at the V now, the external energy. External energy is equal to integral from 0 to L magnitude of the uniformly distributed load multiplied by the displacement field times dx. And that's equal to, again, from 0 to L and transpose times nodal displacement integrated over the length of the member. And you can say that, let's call it F consistent element. And in that case, element will be equal to integral, I have W here, W multiplied by N transpose and integrated over the length of the member, and that will be equal to, again, if I switch the parameters of this integral from -1 to 1, W shape functions transpose times 1 over 2 L times d psi. Okay, so that's the equation for the stiffness matrix, and that's the equation for the element consistent load vector. So P is equal to U minus W. Let's take the first variation. And that will give me from 0 to L K times U and variation in U integrated over dx minus from 0 to L consistent load vector multiplied by the variation in U dx. And that will be equal to from 0 to L K times U minus the consistent load vector, the variation in displacement dx. And again, since the variation U is arbitrary, it's non-zero, we can say that K times U minus the consistent load vector is equal to 0, and that's our equilibrium equation. So I just did that to show you this portion of that equation will give me the stiffness matrix, our classical stiffness matrix definition, because at the end of the day we end up with K times U. And this portion of the equation will give me the consistent load vector. So this portion of the equation will give me the consistent load vector. And it's that part of the equation. Now, with this element formulations, we obtain the equations for the element stiffness matrix and the consistent load vector. And the boundaries of these integrals are defined from -1 to 1. You can either evaluate them by numerical integration or symbolically. So let's go to the next page. So we have k as equal to -1 to 1 ei multiplied by b transpose times b L/2 times d psi. And when you evaluate that symbolically, you will obtain the element stiffness matrix that we derive for a typical plane beam element. Okay. You will get exactly the same matrix. And for the consistent load vector, that's the equation from -1 to 1 W L/2 n transpose d psi. And when you evaluate that consistent load vector, we obtain the following: W times L 1/2 L/12 1/2 minus L/12. So as you see, this vector is nothing but our fixed end force vector. So we obtain the same coefficients as we did in the fixed end forces. So actually this shows us a procedure, right? We start with the total potential energy functional. So this function actually tells me how I can obtain the stiffness matrix and also the load vectors for any kind of element. And when I look at this total potential energy functional, I see that I have the second derivative of the vertical translation, which tells me that if I want to directly use the second derivatives, the displacements must satisfy the C1 continuity requirement, which means that both the displacements and the derivatives of that displacements must be continuous. That's the requirement for the trial function. And for such a case, we have the Hermitian cubic functions. So these are the equations of the Hermitian cubic functions. And when you plot them, you see nothing but the shapes, the deformed shapes that we use while deriving the element stiffness matrix of that beam by using the stiffness method. And then we determine our displacement field. So we have the displacement field, and according to my total potential energy functional, I have to relate the displacement with the curvatures. So I obtain the curvature displacement relationship, basically take the displacement second derivative of the displacement field, and that gives me the beam matrix. Afterwards, it's very straightforward. You write your internal strain energy, instead of the curvature, put your displacement field, curvature field equations, and from that you will directly see how you can calculate the element stiffness matrix. So I just call this portion, the portion without the u's will be my element stiffness matrix, and again in external energy, the part of the equation without the displacement will be my element consistent load vector. So just to double check, I just take the first variation that gives me the stationary condition, or in other words the equilibrium condition for this case, and that directly gives me the stiffness matrix multiplied by the displacement minus the consistent load vector should be equal to 0. That's the equilibrium condition, and this shows me that that part of the equation will give me the stiffness matrix. That part of the equation will give me the element consistent load vector. Now, of course, since we use the exact shapes, exact deformed shapes of the elements to drive for this formulation, at the end of the day, when you evaluate this integral symbolically, you will directly get the same stiffness matrix that you did in the stiffness method. And likewise, when we evaluate the consistent force vector, we get the same fixed and forces that we obtain by solving the governing differential equation for bending deformations. Okay, so of course, since I put the same deformed shape, I obtain the same matrices. There's nothing surprising here, but if you think about it, that shows me the whole procedure. So I can add different types of elements and obtain their stiffness matrices by following this procedure. Now let's talk about the implementation of the Bernoulli Euler beam element formulated with the Hermitian cubic polynomials. Now remember that we interpolated the displacement field as follows. This is the continuous displacement field. I can write it in this form. I is equal to 1 to 4. We have the Hermitian cubic polynomials multiplied by the nodal displacements. And the nodal displacements are defined as Vi, theta I, Vj, and theta j. Nodal transverse displacements and the rotations. Now the cubic polynomials, the Hermitian cubic polynomials, their definitions are here. This is the n1, n2, n3, and n4. Now here you will see the plot of them. So this is the n1 plot, that's n2, sorry, n3. The red one here is n2 and the blue one here is the n1. And remember that the n1 we have a unit translation at the start node and zero translation here. And as you see, the rotations are at both ends are equal to 0. Now when we look at the n2 and if you calculate this rotation, you will see that that's equal to 1. 0 rotation here and 0 translations at both ends. And n3 and n4 are again unit translation and unit rotation. And as we discussed before, these polynomials have the same shape that we use while driving the stiffness matrices. These are given by the deformed shape. We give a unit translation to one of the degrees of freedoms while keeping the rest as equal to 0. And this is the polynomial representation of these shape functions. Now, for the energy interpolation, we need a strain displacement relationship. Of course, for the beam element, the strain becomes curvatures. But I usually call it strain displacement relationship. Now that's so what I did here is symbolically take the second derivatives of these functions. So these are the second derivatives of these 4 Hermitian cubic polynomials. And we know that when we translate the dx to d psi, we have the 4 over L square parameter, and I multiply it with the second derivatives of these Hermitian polynomials, and this is the output, and this is the written in the simple form. So that's what we have in our notes. Now the stiffness matrix, we already derived the equations for it. So basically it's B transpose multiplied with EI multiplied with B and integrated over the length of the member. So I use natural coordinate system, so it goes from -1 to 1, and this is the conversion from dx to d psi. So when you evaluate that symbolically, so as you see, we obtain the stiffness matrix that we obtain by using the stiffness method. So since the shape functions that we use here exactly is capable of exactly representing the deformed configurations, that we assume in the analytical derivation. At the end of the day, with this finite element or the variational formulation of this plane beam, we get exactly the same stiffness matrix. So basically, if your trial function is capable of representing the deformed shape within two nodes, then you will get the exact deformed shape. If there's some level of approximate in these shape functions, then of course you will get a different stiffness matrix here. And I also calculated the consistent load vector. It is the magnitude of the uniformly distributed load multiplied with the shape function itself. So I use transpose here so that I get a vector. Here again, conversion from dx to d psi from -1 to 1. And as you see, here we get the fixed end forces as follows. I have WL over 2 here, WL over 2 here, and a counterclockwise moment and the clockwise moment, and the magnitudes are WL square over 12, WL square over 12. So this is basically the fixed end forces that we calculate for a member under uniformly distributed load. So with the variational formulation, we already get the equations of the stiffness matrix, the response of your structure to deformations, and the energy equivalent consistent load vector. We call it consistent because this equation comes from the energy expression. We equate the internal energy to the external energy, and this is the energy equivalent load vector. And in the future we will see lump vector, which is easier to calculate for some types of elements. And in the lump vector, for example, let me write it here, lumped load vector. This is not energy equivalent, but it is easier to calculate. So if you have a distributed load like this, you just lumped the load to the nodes as follows. You say that that's WL over 2 and that's WL over 2. So these are the lumped equivalent nodal loads. You just apply them to the structure. Here in that case, we calculate the fixed end forces, we reverse their directions and apply to the structure as an equivalent loads.